Describing objects in space. We'll be doing a lot of this. There's three kinds of objects we'll be looking at in this course: curves, surfaces, and solids. A curve is a one-parameter object, just like we did in Calc 2. A surface is new, and it's a two-parameter object, and a solid is a three-parameter object. Two equations give you a curve. One equation is surface. No equation is a solid. This is a curve, and you can mark off values of t for each point. So you're taking the t number line to the curve, and there's a function that's going to do that. Here's a surface, a two-dimensional object, where every point is given in terms of two parameters. So you take a two-dimensional grid, and a function will take that grid onto the object. Solid is a little chunk of space. And you'll take a three-dimensional grid and map that onto the object. The function we'll be using is a vector function. So this is the standard notation we'll use for this course, r, and the number of parameters. A surface takes a two space of parameters onto the object, and a solid takes a three space of parameters onto the object. Let's do the simplest example, a line. 2 points make a line. And we'll label XYZ for any other point on the line. So our goal is to describe what XYZ is. The parametric way is to tag every point with a t value. Then we'll do our vector pushes. I'll push onto the line, so that's my initial t value. And then I'll push along the line. There's my slope vector. Any other point is then just a scale of the slope vector. The resultant push, which is why we use the variable r, the resultant push points to any point on the line. Some books call this the vector x instead of the vector r. So I'm doing the p push onto the line, the position push, and then I'm pushing along the line with the slope vector. That's a function of t, and we use the labeling scheme of the output variable for the function label. Writing down what the vectors are, there's my position vector, scaling my slope vector. Collect together my I components, collect together my j's, and my k's. There's r of t. This is my vector description. For the parametric description, I'm thinking of t building up points on the object. Every point has a t value that's associated with it. I just extract the components of the vector. There's my components for the point. Solving for the parameter in one of the equations and substitute into the remaining two. This gives me the equation form for the line. The equation form is this pair of equations. Every point in 3 space is tested with those equations, and I filter out the line. Here's my parametric description. I'm building up every point on the object with a t value. And then the closely related vector description, the vector that points to a point on the line. Remember from high school that a curve is the graph of a function. In 3-space, it's slightly more complicated. It's the graph of these two equations, these two functions. Every point in space gets tested and either passes or doesn't. Next, we'll do the most basic surface, a plane. 3 points make a plane. We'll describe it the same way we did with lines. We'll start at the origin, push onto the plane as our position vector, and then we'll push to 2 points on the plane. So we have our 2 slope vectors, because a point in 2 lines is also a plane. Identify my pushes. Now, given any other point on the plane, I want to describe it. So I'm going to push to it. So I need to extend the v-axis, I need to extend the w-axis, so that when I combine these pushes, I wind up at the point. The resultant vector is our vector form. The resultant vector always points to the point x, y, z on the object. But I'm thinking about it as a series of pushes. Fill in what the vectors are. Collect components. Collect i's, collect my j's, collect my k's. This resultant vector points to the point x, y, z. So now that we've written it this way, the parametric form is easy. This resultant vector is a function of s and t. Parametrically, s and t go in, x, y, z comes out. I'm building up every point on the object in terms of the parameters. Every point is a function of the 2 variables, 2 parameters. To get the equation form, I need to solve for the parameters. Since there's 2 parameters, I need 2 equations. Once I solve, I'll substitute in the remaining equation. And now it's just algebra. Solving pair of linear equations. I'll get rid of the t first. So I'll multiply the top by 3, the bottom by 2, subtract. And the t's disappear. Isolate s. Now I'll do the same for t. Isolate t. So the first 2 equations rewritten, solving for s and t, are substituted in the 3rd equation. No more parameters. Collect my variables. we'll normally write a plane this way. We'll see why later. The equation form is filtering every point in space through this equation. So the vector form is this, and it points to every point on the object. The parametric form builds up the object one point at a time in terms of the parameters. The equation form filters out space using this equation as a filter.